centerpiece of this presentation is a study that I did back in 2014 on purchased non-chemical fertilizers. We have a very large and active organic growing community in Maine. And there's a lot of anecdotal information about how fast a lot of these materials that are sold that are OMRI-approved materials, how fast they release nitrogen. Things like feather meal and blood meal and cottonseed meal, soybean meal, those types of things that are sold as nitrogen fertilizers to organic growers that are approved for organic production. But I'm also going to talk a little bit about manures and cover crops, compost, and soil organic matter, which are also nitrogen sources. So whether you're conventional or organic, hopefully there's a little bit of information that's useful to you in this talk. So if you Google nitrogen cycle, you're going to come up with about 200 different diagrams with circles and arrows pointing in every different direction. This is a pictorial representation from organic inputs to ammonium to nitrate, and it shows a couple of loss pathways. Here's a better one, a little easier on the eyes, that contains all the inputs, all the cycles, and all the nitrogen loss pathways that there are in nitrogen management. I'm sure you're somewhat familiar with this, but I just want to quickly review it. I have plant and animal residues, fertilizers, manures, primarily in the organic form of nitrogen as inputs into the soil. Those are broken down by the mineralizers, or the decomposers, first into ammonium, and then in a warm, dry soil fairly quickly, within a few days, into nitrate. So the loss pathways in this diagram are in black. So if you have an ammonium form of nitrogen, especially sitting on the surface, it's going to be prone to volatilization loss. It just evaporates into the air as ammonia gas. This is a really common thing with urea when it first converts to ammonium. They've documented 30% loss of what you applied to ammonia volatilization. So that's one loss pathway. Of course, the bigger loss pathways are when it converts to nitrate. This is the form that most crop plants need or prefer, but nitrate it's a kind of a rogue chemical. It doesn't, the soil can't hold it. There are no adsorption sites that hold it. It doesn't form any stable compounds or complexes to hold it in the soil. Essentially, all the nitrate that's there is either taken in by an actively growing plant or it's lost with the next rainfall. And there are two different loss pathways. Because all the nitrate is in the soil water at any given time, if you have water percolating down through from a heavy rainfall, it's going to carry it with it, and that's, of course, leaching. One of the more significant loss pathways in a lot of cultivated ground is where you have water that's not percolating, it's just sitting there. So the soil is saturated, all the pore spaces are full of water, very low oxygen content. There are a number of groups of microbes that can use nitrate as an oxygen source for normal respiration. So they pull the oxygen off, and what you're left with is nitrogen gas, which bubbles off into the atmosphere and it's gone. Either way, you've lost almost all your nitrate. The other loss pathway is immobilization. If you add material that has a lot of carbon and not much nitrogen, microbes are going to go out and find all the available nitrogen that they can to go with all that excess carbon. And 1 million microbes in a gram of soil is always going to outcompete a plant root for available nitrogen. So immobilization gives you this nitrogen deficiency in most of your crop plants. So this is basically the terms that I'm going to be using. Just a little quick refresher on the nitrogen cycle. So that's how nitrogen is held and supplied by the soil, cycled in the soil. That's the source. Here's the sink. This is the nitrogen uptake curve for potatoes. Right your way. So about 30 days after planting, the plants are up and they're starting to take in, and they take in a lot of nitrogen in a hurry. And you have, by 70 days, that crop, here's the total nitrogen uptake on the yellow curve. By 70 days, that crop has taken in 80% of all the nitrogen it's going to for the entire growing season. So you've got this window from 4 to 8 weeks where that crop is just hauling in all the nitrogen it possibly can. It's a front-loaded system. Same thing with corn. This is sweet corn. Field corn will have pretty much the same uptake profile. About 30 days after planting, at that V5 stage, that's when you've got to have nitrogen there in the available form, because that's when you really want, it's going to be taking in the bulk of its nitrogen, again, between about 4 and 8 weeks after planting. So that's the window that you're trying to feed with available nitrogen, regardless of what the source is. Is this 4 to 8 week window, 4 to 8 weeks after planting. So in conventional fertilizers, you have urea, ammonium nitrate, ammonium sulfate, MAP, DAP, your granular chemical forms, liquid forms, UAN, ammonium polyphosphate. These are all chemical forms. Some of them are already in the nitrate. Usually most of them are in the ammonium form, which are going to convert fairly quickly to nitrate. Usually within a couple weeks, depending upon the soil temperature. The more acidifying sources like ammonium sulfate, might be a little bit of a delay because low pH kind of inhibits or slows down that nitrification process. And it depends on oxygen level. Conversion from ammonium to nitrate requires the presence of oxygen. So it's not going to happen in a saturated soil. You need a well-aerated soil. And cool soil temperature will slow it down a little bit, but not all that much. So usually within 2 weeks, you have complete conversion to the nitrate form. But this is way, if you put this down at planting time, this is way before that 4 to 8 week uptake window. And if we get a really heavy rainfall at 2, 3, 4 weeks, does that ever happen? Of course it does, almost every year. All that plant available nitrogen is gone. So what's happened with chemical sources is that they're trying to slow down that release rate, either by adding nitrification inhibitors, urease inhibitors, or by coating the materials to slow down the access of water and the release of these materials. Good talk yesterday on sulfur and resin-coated materials and how slowly their measured release over several weeks or well into the growing season. But just as a bare source of nitrogen, these things are flash in the pan. They release very quickly, and it would be well before that uptake window occurred. With non-chemical sources, you have at least a little bit of luxury of somewhat slower release. And what I'm going to talk about today is spend some time on some of these purchased plant and animal meals that are sold primarily to organic gardeners. A little bit on animal manures, cover crops, and then at the end compost, and a little bit about soil organic matter, which is also another source of plant available nitrogen. So in the last 5 to 10 years, there have been a few studies done as organic production has really caught on nationwide. There's a lot of these materials that are sold. They have a fertilizer guarantee for nitrogen content, but there's a lot of anecdotal information, a lot of conventional wisdom about how fast they release. And so there have been some studies done to determine the release rates of at least a few of these materials, and there are more and more every year. There was one done at Michigan State that looked at the effects of temperature and moisture content on release rates on a very limited number of materials compared to chemical release. There was a Cal Davis study that looked at soil temperature effects But their primary concern was looking at short-term release. They were looking at suitabilities of these materials for mid-season side dress. So they only went out to like 4 weeks of release time on a fairly large number of materials. Oregon State did a very extensive study over several years. They did laboratory incubations. They did field studies, very extensive study, but they were looking at fairly high soil temperatures. Heather Darby at University of Vermont did a limited study in 2012 looking at the effects of soil texture on some locally available materials. This was about all I could find ahead of time. Either they were looking at a limited number of materials or very short duration, and I was interested in our cooler soil temperatures in Maine and a lot of new materials that were coming down the pipeline for use that were approved for organic production. So I ran my own incubation, and what I was looking at, why I was concerned with temperature was, this is some data from the Michigan State study. And this was 15, 20, and 25 degrees centigrade, 3 different incubation temperatures. Here's the urea source, the chemical source over here. You see there's basically no effect in temperature on urea whatsoever. It all, regardless of temperature, released quickly, very quickly, and fairly completely. The non-chemical sources, this was alfalfa pellets, blood meal, and partially composted chicken manure. And they had obviously a very significant effect of temperature on release rates. Cooler temperature, slower release, less complete release, higher temperature, a little bit faster and a little bit more complete. So temperature obviously has much more of an effect on non-chemical sources than it does on chemical sources of nitrogen. This is a daily temperature map. It's online through Syngenta puts this up. I think it's greencast.com. This is from the end of July 2014, and the key is at the bottom. The light green is 55 to 60, yellow is 60 to 65, and orange, light orange is 65 to 70. So you see up here in New England, and especially in Maine, our soil temperatures are in the 60s, and this is the end of July. Okay. Further south, down here where you folks are, you're up into the 80s. All right. So a lot of the studies that were done at warmer soil temperatures than what we have in New England. We had some heat in the first part of August, and you see our soil temperature got up early up into the 70s, and a couple weeks later we were back down in the 60s again. So we have a lot cooler soil temperature up north than you do down here. And here you're in the 70s and 80s down where we're standing now. So quite a difference in soil temperature. So my interest was to look at cool soil temperature for an entire growing season, 16 weeks, with some locally available materials. I mixed, ground up the fertilizers, mixed them with soil at a rate to give me 100 parts per million total nitrogen. In addition to the soil, that's 200 pounds per acre. Incubated them at constant temperature in the tubes, and then, in intervals, I pull the tubes out, extract the plant available nitrogen, and measure it. This is toward the end of the study. Actually, there was just 2 weeks, two different readings left in this incubator vessel. This is what I found. I used feather meal, blood meal, soybean meal, alfalfa meal, fish meal, corn gluten, which is used for the quote-unquote organic turf management industry, broiler manure, which I think you're familiar with. This is the pelleted stuff. There are several different pelleted broiler manures that are sold. Microstart from Purdue, Cheap, this is NutriWave actually. Nature Safe, which was a new material. It's a combination of feather meal and meat meal, 13% nitrogen. And then I used urea and ammonium sulfate as chemical comparisons. So this is the actual total nitrogen content here. Quite a range from the natural sources from 3 to 14%. And I applied these to the soil, assuming whatever they had as a label guarantee. When I actually measured the actual content, you can see these actual applied nitrogen is, plus or minus 100. I was targeting 100 parts per million, 200 pounds per acre. And this is the amount of total N that went to the percent of the total N that went all the way to nitrate at these time intervals. If you graph it out, here's the urea, light blue, very fast release, even at cool temperature, similar to the Michigan State study. By 4 weeks, all the nitrogen that was going to be released from urea was there. If you don't get 100%, you always have a little bit of volatilization loss. But urea was all done by 4 weeks. Ammonium sulfate took about another 2 weeks because it's so intensely acidifying. It slowed down the process a little bit, but by 6 weeks, it was all done too. So we have a whole group of fertilizer sources that track each other very nicely in the non-chemical sources, and it's kind of busy here, but blood meal is usually the gold standard for a fast release organic nitrogen source. Everybody knows that blood meal is a fast release. Well, all of these other materials track blood meal very nicely. Feather meal, soybean meal, fish meal, corn gluten, Nature Safe, that new material, they all track blood meal very nicely. Now, this was kind of the crux for the organic folks because everybody knew that feather meal is slow release. It's not. It's just as fast as blood meal. Most people thought that soybean meal releases fairly slowly. It does not. It's just as fast as blood meal. What is slow, or slower, is green down here is alfalfa meal, and the brown is broiler manure, something you folks are familiar with. So these two released much more gradually. It took them an extra 4 weeks to finally plateau out. So what's different about those two? Well, if you go back to the characterization data, not only did we measure total nitrogen, we also measured total carbon and looked at the carbon-nitrogen ratio. And you notice alfalfa meal and broiler manure are the only two that have a carbon-nitrogen ratio greater than 10 to 1. So there's something about that 10 to 1 ratio that's pretty critical. And in fact, Heather Darby's limited incubation, a couple of years before, she found the same thing. She got much better mineralization from materials that had less than a 10 to 1 carbon-nitrogen ratio. And the further above 10 to 1 you went, the slower the mineralization rate. So not only is temperature critical to release rate, but so is carbon-nitrogen ratio. So how did all this data compare with all these other studies? Well, here's my data here. This is materials that were in common. This isn't all the ones that I ran, but the ones that were in common with the other studies. Feather meal, blood meal, soy, alfalfa, fish. That's a blended fertilizer, North Country Organics, that I didn't mention before. Broiler manure is down here at the bottom. And you'll see these materials all line up very nicely. The low CN materials were all around 50, high 50s, low 60s release rate. Soybean meal the same. Alfalfa was lower. I got 25%. Oregon got 11%. Fish meal was up around 50, 60%. And the broiler manure was all down in the 20s and low 30s. So everybody's data lined up very nicely. Especially with Oregon State. I had really good agreement with them. There's a difference here. It took me 8 weeks to get to 60% release on these faster release materials. It took me 8 weeks. Oregon State got there in 4 weeks. Okay, so they got there in half the time. I incubated at 60 degrees Fahrenheit. They incubated at 72. So 12 degrees Fahrenheit effectively doubled the release rate. Between what Oregon ran and what I ran, we got the same numbers, but it took me twice as long at a lower temperature. So that really points out the effective temperature on release rates as well as carbon-nitrogen ratio. That was, was very reassuring for one thing. But after we'd done all these studies, a colleague of mine at Rutgers said, I found this old study from Rutgers from 1942. Here's their data here. There were 3 or 4 things in common, and son of a gun, all their numbers lined up with everyone else's. So they figured this all out 70 years ago, and the rest of us just keep doing it over and over again. But with new materials, of course. And this is a chart from their publication from 1942. They were looking for, I assume, looking for non-chemical sources during the war. And they were looking at locally available nitrogen sources, and some of them are in common with what we have today. Some of them are stuff that you just don't get anymore. Soybean meal, cottonseed, castor, cocoa, alfalfa, blood, fish scrap or fish meal. And they've also found in 20-day and 40-day release rates were very dependent on carbon-nitrogen ratio. So the low carbon-nitrogen materials release 50–60%. The higher carbon-nitrogen materials, here's alfalfa meal at 20%, or 20–21 carbon-nitrogen ratio, only release 20 and 30%. Wheat straw, 200–1 carbon-nitrogen ratio, lost nitrogen. There's immobilization from high carbon-nitrogen material. Hoof meal, I don't think you can get that anymore. That was 3–1 carbon-nitrogen. That released almost 70%. Blood meal, 3.5, 60%. Fish meal, 60%. Bag guano, 1.3–1 carbon-nitrogen ratio. Very low CN ratio, released 80% in 20 days. Really low carbon-nitrogen ratio. Horse manure, this is bedded horse manure with wood shavings, 33–1 carbon-nitrogen ratio. Immobilization, they lost 20%. So this really points out the importance of carbon-nitrogen ratio and how fast non-chemical sources release. I just wanted to mention one of the things that came out of the Oregon State study was this calculator. This is a free download. If you go to this website, you can free download. They ask you a couple of questions. Are you a commercial grower? Are you a consultant or whatever? But it's a free download. It's an Excel spreadsheet. This has all of the results from their incubation studies, and they have plant available nitrogen at 28 days, at 4 weeks, and in full season. And then they have some of the secondary and micronutrients in there as well. There's another tab that shows, that has where you can plug in the pounds that you've applied, and it draws on this table to tell you how many pounds of plant available land you're going to have in 28 days and in full season. It's a pretty slick little calculator. Pretty handy if you're using much in the way of organic nitrogen sources. So much for the purchased materials. Now for manures. And manures are slightly different in that they're partially mineralized already. Part of the total nitrogen in most manures is already in the ammonium form. Not quite to nitrate, but almost. So as you would expect, ammonium is going to break down and release once it's applied and incorporated. That's going to be pretty quickly available. The remainder of the nitrogen is in the organic form. And we'll talk about release rates on that shortly. This is from a UK study. They had 2 different sites and a source of these 5 manures at each of the 2 different sites. And this is the carbon-nitrogen ratios in green. So bedded manure is around 14:1. Bedded swine manure is pretty close to 10:1. Poultry layer, this is layer manure, not broiler manure, has a much lower CN ratio, 4 or 5:1. Liquid cattle manure, they had one source that was 5:1 and another source that was almost 10:1. And the liquid swine manure was only 2:1 and 3:1 carbon-nitrogen ratios. And on average, this tells you about how much of the total nitrogen was already in the ammonia form. For bedded manures, pretty common, about 10%. We run 300 or 400 manures through our lab every year, and this pretty much lines up with what we find on average. Poultry layer, almost half of the total nitrogen is in the ammonia form at application time. Liquid cattle manure, pretty typically about 50% is going to be already in the ammonia form. And the swine manure is really hot stuff. That's 75% of total N. This stuff is pretty much all ready to go as soon as you apply it. So the ammonia nitrogen is going to pretty much release like a chemical fertilizer. Only takes 2 to 4 weeks for that ammonium nitrogen to be converted all the way to nitrate. It's going to be pretty immediately available. Soil temperature can slow it down a little bit or speed it up, but because it is a microbial process. So what's left is the organic nitrogen. And somewhere around half of the organic nitrogen that's going to be released the first year is going to happen just after the ammonia mineralizes all the way to nitrate. Now I'm painting with a wide brush here, and definitely you're going to have an effect of soil temperature and carbon-nitrogen ratio on how fast that organic nitrogen releases. But the thing with manures, and this has been very well studied, is you not only get some release of nitrogen from the organic fraction the first year, but also a little bit the second year, and even a small amount the third year. So I just pulled a couple of manure management guidelines, one for Vermont and one for New York. This is Vermont's manure management guideline. The first year from liquid manures, you're going to get about 25 or 30 or 35% of organic nitrogen released the first year. A little bit less for solid manures. And second year, somewhere around 10%. And then the third year, just another 3 or 4%. Here's Cornell's guidelines, pretty much the same as Vermont's. They do add poultry manure. So you've got 55% of the organic N is going to release the first year on average, depending upon the source. This is layer manure. So 50% of the total N is in the ammonia form, and the other 50%, half of that's going to release. So you're going to get 75% of the total nitrogen from layer manure released the first year. Fairly complete. 35 for liquid, 25 for solid, 12% the second year, 5 the third. Those are the credits that they give for manure application over 3 years. And this is pretty much reflected in the UK study. This is what they found over 3 years. This graph covers 3 years. The first year ends, well, they applied in March. The first year ends December year 1, May year 2, October year 2, and then here's year 3 here. So they took the 2 manures that had one that had the lowest carbon-nitrogen ratio and one that had the highest carbon-nitrogen ratio. The swine manure having the lowest carbon-nitrogen ratio, you get a big release, almost 50% the first year of organic nitrogen. Second year, about another 10%, and the third year, maybe another 2 or 3. The bedded cattle manure that had the highest CN ratio, you only got about 15% the first year. And another, probably 3 or 4% the second year, and maybe 1 the third. So carbon-nitrogen ratio makes a big difference, not only the first year, but in continuing years on the manure. The rest of it kind of gets folded into the soil organic matter. Some of it's lost to volatilization, but these are the plant available release rates of organic nitrogen and how it depends on carbon-nitrogen ratio. Cover crops. There are a whole lot of different cover crops with different nitrogen content, different carbon-nitrogen ratios, but for nutrient management or for fertilizer recommendations, typically you'll be asked, is this after a sod crop? If so, you'll usually get a nitrogen credit. And just, as an example, this is Cornell's nitrogen credit for plowing down a sod crop for corn or some other crop. For grass sod with no legume, they're saying 50 to 60 pounds of nitrogen released. Now, all the nitrogen in a cover crop is going to be in the organic form, unlike manures where you have some partial mineralization. So this is all organic nitrogen mineralization, 50 to 60 pounds just from grass sod. For a fairly weak legume grass stand, somewhere around 100 pounds per acre the first year. And if you have a really strong legume stand, 3 or 4 years old, good stand of alfalfa or clover or vetch, you're going to get 120, 130 pounds of nitrogen. Now this is in New York, where the soil temperatures are on average a little warmer than in Maine. In Maine, we don't give this quite as much. So for grass sod, we're going to give about 40 pounds credit. For a 50% legume stand, about 75 pounds. And for a 100% stand, 90 to 100 pounds. That's to compensate for our somewhat cooler soil temperatures. So these credits really depend upon not just the species that you're plowing down, but also your normal mineralization rates for your given soil temperature. And of course, that's going to vary from year to year. So these are generalities. And somewhere around in cool soil, it's going to take 30 to 50 days for about half of the nitrogen to release. By comparison, this is nitrogen release from cover crops in California, another Cal Davis study, and you're getting some pretty serious release right at about 2 weeks, and then it extends out to about 6. So this is 2 to 6, but this is at fairly warm soil temperature. These are like organic fertilizer mineralization curve here that pretty much shadows the fertilizer curve as far as timing of release in a warm soil. Here's the actual nitrogen uptake window, that 4 to 8 week window. So it's a little bit before. You don't get really perfect correspondence. But you'll notice it starts abruptly and then kind of tails off over here. Now the length of that tail is going to depend on soil temperature and carbon nitrogen ratio. So the higher your CN ratio, the longer this tail is going to be out into the uptake window, the plant uptake window. So this is a generality, and you've got this long tail. It's not perfect correspondence, but you can, if you delay incorporation of a material until it's a little higher carbon nitrogen ratio, you're going to get a more extended release than what's shown here. Here's a crop residue carbon nitrogen chart that was on an NRCS soil health website. And you can see for grain straw, you're up in the 70 to 80 to 1 carbon nitrogen ratio. You're going to have a mobilization from that, at least temporarily. Corn stover isn't much better. A mature rye crop is getting down to about a little under 40 to 1. An actively growing rye crop is going to be around 25 to 1. You get down in here to the manures, and you're down around 20 to 1. And here's your legume hay, beef manure. Young alfalfa hay is about 13 to 1. That's it's the same as the alfalfa meal was 12 to 1. Now this says soil microbes are about 8 to 1. And that's the whole key with why is that 10 to 1 ratio so critical for nitrogen release? And that's because most living cells have a carbon-nitrogen ratio, whether it's microbes or you or me, we're about 10-to-1 carbon-nitrogen ratio, or 8-to-1. So since that's what our content is, that's what we need to take in. So the microbes are looking at material that's being fed to them. If there's more carbon than they need to go out and find more nitrogen somewhere to go with it to maintain that 8-to-1 or 10-to-1 carbon-nitrogen ratio. So if you're feeding them something that's less than 10-to-1 CN ratio, they have a little bit of an excess of nitrogen proteins, and therefore they're going to release it faster. If you feed them a whole lot of carbon and not much nitrogen, then they're going to go out, at the very least, they're going to release nitrogen more slowly. And at the worst, they're going to go out and grab nitrogen to go with all that extra carbon and wind up immobilizing nitrogen. So just as a summary, nitrogen release on fresh organic material. This is the materials we've talked about so far: purchased plant and animal meals, animal manures that are uncomposted, cover crop residues. If it's less than 10-to-1 CN ratio, you're going to have relatively rapid release. Most of these materials don't have on the label or on the analysis a % carbon. So how do you figure out carbon-nitrogen ratio? Well, in some ways you don't absolutely have to, because most plant animal material, manures, cover crops have total carbon content somewhere between 40 and 50%, pretty uniformly. So if you figure 50% carbon, all you need is 5% nitrogen to have a 10-to-1 carbon-nitrogen ratio. So if your material has more than 5% total nitrogen, you're probably pretty safe in assuming that the CN ratio is less than 10-to-1, and it should release fairly quickly. So not only do you get more nitrogen if it's above 5%, but it's going to release more quickly. It's a good rule of thumb. Now, I'm talking about dry weight basis. Okay, so if you try to, if you look at a manure analysis and it says, like 3% nitrogen, that's on a as used or as spread basis. You need to back calculate that to a dry weight basis, because that 50% carbon I was talking about is in the dry material. Okay, so layer manure typically is around 3% as spread, but it's 50% moisture. So actually on a dry weight basis, that would be 6% nitrogen. That puts it up over that 5%. Carbon-nitrogen ratio is less than 10-to-1. That's why layer manure releases so quickly. So if you want a really quick and dirty way of figuring carbon content, just look at the % nitrogen, figure everything on a dry weight basis. And that should give you a pretty good indication of carbon-nitrogen ratio. So less than 10-to-1, fairly quick. Between 10 and 20-to-1, it's going to be much more gradual. Between 20 and 40-to-1, you're kind of on the ragged edge between releasing any nitrogen at all or tying it up. Certainly by the time you're over 40-to-1, you're going to have nitrogen immobilization. Temperature effect. For each 14 to 18 degrees Fahrenheit, which is 8 to 10 degrees centigrade, you're going to roughly double the release rate of nitrogen from any of these materials. So if you look at articles on nitrogen mineralization, often they'll mention this factor that's called a Q10. This is the change in mineralization rate for every 10 degrees centigrade increase or decrease in soil temperature. So Q10 values in mineralization studies generally run between 2 and 3 times. Now, Oregon State doubled my mineralization rates with an increase of 7 degrees centigrade. Okay, so that if you expand that from 7 degrees to 10 degrees, the Q10 difference between us was 2.8, which is right down the middle of this 2 to 3 times. So everything lined up nicely. But a Q10 value is typically every 10 degrees centigrade or 18 degrees Fahrenheit is going to at least double the mineralization rate for any of these materials. So far I've been talking about materials that are fresh materials. They haven't been degraded. Compost has already been through a microbial degradation process in the compost pile. Same thing with soil organic matter. That's really been processed heavily, and you're left with this residual humus material, which is extremely useful for soil quality, and it does supply nitrogen, but all of the rules that I just talked about, carbon-nitrogen ratio, and to some extent soil temperature, but mostly carbon-nitrogen ratio guidelines just kind of go out the window, because we're talking about material that's already been degraded, and so it doesn't release as quickly, anywhere near as quickly as any of these other materials. So at the same time I was running an incubation on these purchased organic nitrogen sources, one of the grad students in our department was doing a compost study and doing an incubation, soil incubation with 4 different types of compost: beef manure, food waste, dairy manure, and poultry manure composts, 4 different sources, mixed with soil at 320 parts per million, 640 pounds per acre equivalent total nitrogen content. She incubated at 20 degrees centigrade or 68 Fahrenheit for 8 weeks and looked at the nitrogen release profiles from these 4 different sources of compost. So here we have 4 sources. Their carbon-nitrogen ratios for compost, these were quite good, 14:1 up to just under 18:1. Pretty typical finished compost carbon-nitrogen ratios. 2 of these composts at time 0 had a pretty substantial amount of their total N already in the plant available form. Not because of the source of the material, the feedstocks, but because of how they were composted. They were composted under cover, which means the nitrate that was produced in the composting and curing process was maintained in the material. Most composting operations are outside, and as they sit in the pile, rainfall goes down through, and the plant available nitrogen, the nitrate, what happens to it? It gets washed out. So these are 2 fairly typical composts and 2 atypical composts as far as the starting amount of plant available nitrogen. But graphically, you can see that from time 0 to week 8, over that 8-week period, each one of them, regardless of the source, only released about 5% of the organic nitrogen at a fairly warm soil temperature. So the ones that started high, here's at 23% for the poultry manure compost, only went up to about 26%. Okay, so only about 4 or 5% of the organic nitrogen content in any of these 4 composts was released over an 8-week period. And soil organic matter is down here. That only went from about 18 parts per million of nitrate up to about 36 parts per million. So we did get some plant available nitrogen out of it, but as a percentage of the total N, it only went from about 1% to 1.9%. So you do get release of plant available nitrogen from these materials that have already been through a degradation process, but it's very, very slow. So my stock answer to most people, especially gardeners who think that compost is complete fertilizer, is that it's not. Okay, it's a lousy source of nitrogen. I'm sorry, but that's the way it is. If you're lucky enough to get some with a starter amount in it, you will get some benefit from it, assuming that you can get it on and feed that 4 to 8 week uptake window. But it's pretty rare that you're going to find a compost that has a good starter amount of plant available nitrogen. Most of them are going to start out here at 0, and they're going to give you about 5% release. And if you extend this out to 18 weeks for a full, or 16 weeks to a full season, maybe you'll get 15%. I think for nutrient management guidelines, usually you can take a credit of about 20% of organic nitrogen release on compost in most states. So just to summarize here. BMPs for nitrogen management, pretty much the same as you would for chemical fertilizers. Nitrogen management is going to be different every year. You need to be adaptive. You need to be able to use multiple sources at multiple times because every growing season is different, and we get these increasingly erratic, heavy rainfall events. You're going to have better efficiency in warm, dry years, less efficiency in cool, wet years, and a high potential loss of nitrate in heavy rainfall events. So obviously you don't put nitrate form nitrogen on at planting time. You're just asking to lose it in that 4 weeks between planting and when uptake really gets started at 4 weeks. So you just figure that your low CN materials are going to release quickly. Your higher CN materials are going to release more gradually and further into the growing season. And don't count on compost to give you a whole lot of nitrogen. So split applications, count on your organic matter and compost if you're using it to give you a very slow, gradual release over the entire growing season. If you want to put something on at planting time, use something with a little higher CN ratio like broiler manure. It's a good at-plant source because it's going to release over 8-10 weeks at least. I think the one that I ran, it plateaued at 12 weeks when it finally stopped releasing. But that was at a cooler soil temperature. PSNT, or ear leaf, just before that rapid growth stage, find out, that's the point where you need to find out whether you need to supplement N or not, and then go on with a fast release, low CN or a chemical source, 30 to 40 days after planting, just before that 4 to 8 week uptake window. If you could include a legume cover crop in the rotation, that could supply a lot of your plant available nitrogen. Good organic practice. A lot of our organic growers are growing rye vetch or peas and vetch or a clover crop just before their heavy nitrogen feeding crop in rotation, and they'll plow that in. And a lot of them don't need to supplement at all the next year. And the higher the carbon nitrogen ratio of the material you're plowing in, the more extended release you're going to get further out into the growing season. Cultivated soils typically have a pretty major traffic pan, a tillage pan. And this is impervious to infiltration, water infiltration. And if you can't rip up that layer and poke some holes in it, you're going to wind up with these 3, 4, and 5 inch rainfalls with soil saturated for several days afterward. And you're going to wind up with a lot of denitrification loss. We found out that denitrification is a lot faster, certainly faster than I thought it was. We found out that we could have complete denitrification of what we had a soil that was over 100 parts per million nitrate. And we lost all of it just by leaving that soil saturated over one night. Okay, so in 24 hours, we could have complete loss of nitrate to denitrification. It's that fast. So if you've got a traffic pan or a tillage pan that's going to perch that water table, keep it from percolating down through, if you're going to have saturated soil for 2 or 3 days, you've lost all your plant available nitrogen. 100%, almost 100% guaranteed. So, of course, if you improve infiltration by either ripping or planting a cover crop that can poke holes in it, like sweet clover or tillage radish, yes, you will have more leaching loss, but at least you're not going to probably not lose as much or as fast that way as you will with denitrification. So that's about all I have. Be glad to answer any questions. Yeah.
Whenever you have this kind of CN ratio, when do you that does come back like your cover crop?
that?
Whenever you have a acid ratio like the cover crops, how do you determine when that does eventually come back? Or is available?
It will be available. It's just going to take to extend the release.